So welcome everybody to our very first 2017 OTS Connect session on the Hour of Code. And beyond the Hour of Code. And it's always great to see people from all over Ontario that participate in these sessions with OTS Connect. And we're here with Brian Aspinall, and he is a professional on integrating coding with his students, really inspirational and very exciting to see what his kids are doing. So I'm going to turn it over to Brian to introduce himself and leave you in his awesome hands.
Well, thank you for that brief introduction. What many people don't know, I studied computer science, so I'm very, very biased in terms of teaching it in the schools. I remember what it was like for me in university a little over 15 years ago now. I mean, people ask me about my experience in university, and I often say, we never really wrote a lot of tests or exams. We were always told to solve authentic problems using computer code. My final year sort of thesis project was to write software for the biology department to track the behavior of fish. So I've always had this, that's always sort of been my pedagogical approach to teaching. And this would be my 10th year of teaching. I'm actually on a leave of absence working with Fair Chance Learning as Program Director of STEM Education. And our mission is to support Ontario, our ministry, and all of you fine folks with integrating coding into existing curriculums rather than seeing it as an add-on. It's kind of a new literacy that we can incorporate into things that we already do. And I hope to share some examples of things sort of, I'm doing the air quotes right now. I know you can't hear me. That's one thing about webinars is I act it out still. My dogs look at me funny, but the air quotes around the traditional lessons, things that I used to do in my classroom that I just kind of rebranded that fall underneath that sort of computational thinking umbrella. So I named this slide deck Beyond the Hour of Code just because I think the Hour of Code is a wonderful, wonderful entry point, but it's not a destination. And quite often we see people stopping there. It's an isolated 40-minute lesson. It becomes kind of an add-on in the computer lab, which is very contradictory to what Seymour Papert would have suggested back in the 70s and 80s. So I hope to kind of raise awareness around computational thinking, some core competencies for the 21st century, two being thinking critically and thinking creatively, and how we can get kids to do both of those things in all of our content areas using STEM or STEAM or coding kind of as that driving force, if you will. So I'm going to go back to my first year teaching around 2005. Reason being, I haven't necessarily shifted pedagogy in my practice because it was kind of a goofy pedagogy to begin with, and I'll tell you why. I mean, we always teach to our strengths. And so in 2005, like I said, here's this computer science major who's landed a grade 5 LTO. I have no idea how that happened, but it did. And so I thought, you know what, all the sports teams are taken care of. I'm the new person at the school. I want to do some extracurricular stuff. So I thought, we're going to do this coding club, right? 2005. And so it's taken 10 years now to see coding clubs come into existence. In my experience, if you had asked somebody like Seymour Papert, he would say it's taken 50, 60 years to see coding clubs come to life. But anyway, so around 2005, I had some intermediate students. They said, we want to make this game. And there's quite a few of you in the chat who've heard this story, and it never gets old in my opinion, but these boys said, we want to make this game. And I had written thousands of lines of Java when I was in university, but I'd never actually seen Scratch. And so it's interesting to point out that Scratch is actually 14 years old. It's kind of a really old technology developed in 2003 on the principles of 4 Ps. We talk about Cs today, 6 Cs or 7 Cs. 2003, the 4 Ps were projects, passions, peers, and play. And for a lot of us in education in those days, we weren't necessarily ready for that. I mean, we were filtering the internet and shutting it down, so the whole notion of collaborating in a digital space was kind of non-existent. play-based learning had been around for a long time, but we hadn't really seen it, particularly in Ontario, until play-based learning in kindergarten. And I'll talk about Reggio Emilia and play-based learning dating back to World War II, but in terms of, mainstream education in 2004, we weren't quite ready for that. In terms of projects, well, in my experience at least, there was a lot of projects, but they were a lot of directed projects. They weren't as open-ended as they are today with concepts like Genius Hour and passion projects. So anyway, back to scratch and hanging out with these boys in the computer lab, and they said, we want to make this pooping baby game. And I said, I'm not sure if that's entirely appropriate, but the reality is nobody's going to have any clue what the heck we're doing in this computer lab, so I'm all for it. So we're playing in Scratch. I'm sitting beside them on the computer. I'm learning the tool for the first time. I understood the concepts because they're very similar across, regardless of programming language you choose, whether it's block-based or whether you're writing syntax. The concepts of computer science are all the same. So anyway, the boys are making this baby scroll back and forth across the top of the screen, and they're firing poop missiles down towards the bottom. And I'm trying to follow along the process. Like, how did you make that baby move to the right like that? And they said, well, it's easy. You go change x by 1. So I went change x by 1, and I ran the program, and the baby moved 1 unit to the right. I thought, oh, that's pretty cool. How did you make it move to the right forever? And as soon as I said that, I realized I had to put it in a loop. But I didn't tell them that. I wanted them to tell me that. I was hearing about this whole flattened classrooms and co-learner concepts. A lot of people were talking about that on social media. Not quite Twitter, because we weren't quite on Twitter in 2005. But I said, okay, I'm going to change x forever by 1. I ran the program, and the baby moved to the right side of the screen, and I kept pulling it back and letting it go. I was so amazed that I actually made this baby do that, particularly because studying Java in university was a very much syntax console-based programming language. It wasn't there was no, like, graphical interface, if you will. So I said, how did you make the baby go to the left? They said, Mr. A, you're killing us. It's a change x by -1 forever. And I thought, oh my goodness, this is amazing. Okay, you got to tell me about the poop missile algorithm. What does a poop missile algorithm look like? And they said, well, the baby's always broadcasting its location. I'm at +200, -100. I'm at +300, -200. And the poop missile goes, okay, I'm on my way, and it plots itself at that position at a random timed interval, and it flows to the bottom of the screen. And I thought, okay, hold on a second, everyone. Let me reiterate what you just said. Again, I was an LTO trying to learn, trying to know everything I could possibly know about Ontario curriculum, so I was relatively familiar with intermediate curriculum, and it sounded a whole heck of a lot like geometry. I said, boys, I'm going to paraphrase what you just told me. You have a baby at a constant x position, translating from the right to the left by changing its x value from positive to negative. You're making it actually flip or rotate when it touches the perimeter of the screen. The poop missiles are plotting themselves at the baby's location and then translating to the bottom of the screen using a negative y value. And then you, as the user of the game, has to catch the poop missiles to save the city. For every poop missile caught, you get a point, and you store it in a variable, so we're kind of talking about algebra. And they sort of looked at me, and they said, well, yeah, I guess. And I thought, oh my goodness, this is amazing. And here we are doing actual curriculum in an after-school coding club, building this game that I'm not entirely sure is school appropriate in 2005. And I'm watching these boys construct their own knowledge of pretty well the entire strand of intermediate geometry without any explicit teaching. So I'm so excited, and I drive home that night, and I thought, I'm onto something. I need to investigate this Scratch platform and figure out what the heck Scratch is and why it exists. And I realized, I'm going to actually go back a little bit further. This is where I first learned about Reggio Emilia and play-based learning that was started in towns in Italy after World War II, where schools decided kids should learn differently because the world is changing. And we should have kids learn like a Montessori-based style by constructing their own knowledge of the world around them. So as I'm learning about Reggio Emilia, 30, 40 years prior to my pooping baby experience, talking about having kids learn through play. I start to explore Piaget's work and his idea of constructivism. Kids learn by making mental models of the world around them and through digital experiences. And he didn't say digital, I'm throwing that in there now. Through unique, kinesthetic, hands-on, authentic experiences. And I learned by researching these individuals that Seymour Papert, was actually a student of Piaget, and Piaget once said, no one understands my ideas as well as Seymour Papert. And I thought, I need to figure out who this Seymour Papert individual was. So I started to look on the internet for Seymour Papert, and I came across Mindstorms, the book he had written in 1980. And if you read it by today's standards and you didn't know it was written in 1980, it would sound very much what we're talking about here on this webinar, and what the themes are in education by today's standards. Unfortunately, Papert's work, it didn't catch on sort of mainstream in his time. Unfortunately, he passed away last summer. He was a bit of a disruptor in education. He said things like, get rid of the computer lab. We don't go to the pencil factory to learn about pencils. The computer is a tool for learning that should be accessible to kids at any given time. It shouldn't be in rows in the computer lab where kids are set in quiet settings and all told to do the same thing on a timed, scheduled event once a week. That's not what the purpose of the computer is about. Unfortunately, in many cases, the personal computer was so expensive, right, in the 80s, the 70s and 80s, and so we only saw them in isolated computer labs. And from a clerical standpoint, that was kind of the only way we could manage those situations. So I learned from Seymour Papert, who actually started the MIT Media Lab. He had actually started the first block-based coding language in 1967, and he called it Logo, and he believed that kids should learn about geometry through kinesthetic activities. He would have kids act out situations in the room, like, I want you to find the perimeter of this space by walking it yourself and using your own footsteps as a unit of measure. And that's pretty radical in 1967 when you think about a traditional lens of schooling with that one-size-fits-all sort of experience. But Papert believed if kids could act out these situations kinesthetically and then replicate it on the computer, not only had they grasped the concepts, but they demonstrated mastery through application. Papert wasn't necessarily talking about throwing out grades like many of us now today are, but he was certainly on the same sort of, definitely way ahead of his time by talking about some of those concepts. And I just want to share this with you because today we have Scratch, and Scratch was developed by Mitch Resnick, like I had said earlier, in approximately 2003, 2004. But what's so interesting to know about Mitch Resnick is he was actually a student of Seymour Papert. So now we've got the continuum dating back to Reggio Emilia, World War II, Piaget, Seymour Papert, and Mitch Resnick. And so now today we're talking a lot about Scratch, and we're talking a lot about Scratch Junior, and there's hundreds, if not thousands, of clones of those programs in the app stores on all of our platforms. And so we're starting to see their work finally come to fruition. But it's actually moving significantly fast, and it hasn't stopped with Mitch Resnick. Eric Silver and Jay Rosenbaumer were students of Mitch Resnick's, who took to Kickstarter because that's the world that we live in about 3 years ago. And they said, we want to kickstart this device called a Makey, which is a keyboard interface, allowing students to create electrical circuits in a physical space so they can actually interact with the digital content they create in Scratch. And so if you think about it like a layered cake, we've got simply playing in Scratch, developing in Scratch, simulating theories like the particle theory and science in Scratch, and then connecting it to a hardware tangible where kids have to inquire about what conductors are by building circuits. We're able to continue the motion, the movement of this constructivist approach to learning. So Eric and Jay jumped on Kickstarter and said, we have a dream. We believe everybody is an inventor, and we want to bring this product to life so kids can use this device called Makey to actually engage and build really cool things. And they were successful with it. Interesting fact, one of their classmates, and I'm sorry, her name, I forget her name at the moment, but one of their classmates also kickstarted Little Bits and was successful. And so Little Bits is another inventor's kit that you can actually purchase today. I'm going to go back now just because it's important to come forward full circle to the pooping baby story. As I'm learning about Mitch Resnick, because Scratch was only a year or two old at that time, and I'm learning about Piaget and Papert, I come across this term called computational thinking, which is somewhat of a buzzword by today's standards, but it was actually defined in 2006, 2005, 2006 by Jeanette Wing, who was working with Microsoft. And she wrote a wonderful article. It's only 2 pages long, and it's like 16-point font. I swear she wrote it for dudes, and I'm so grateful for that because I've read it a bunch of times now. It's a quick read. But in it, she defines computational thinking as a skill for the future, no longer a skill just for computer scientists, but society at large. She was talking about problem solving with technology and Internet of Everything, or Internet of Things, which we're about to cross into now in about 2020. And she was talking about having people become problem solvers by using technologies to create solutions instead of just finding solutions. And it makes me think about things I've done in my own classroom where the answers were always available, whether it was through internet search engines or the back of the textbook. How can I, in my own practice, provide opportunities for kids to create solutions, to do things that have never been done before, and what does that look like? And so through my master's course, I've started to revisit Jeanette Wing's work, but I came across a really, really fascinating Venn diagram, and I'm happy to share this after the fact. It talks about mathematical thinking and some of the sort of, I'm using the air quotes again, those rote learning traditional lessons in a math class, as well as computational thinking, and then the intersection of those, right? Ultimately, we want our kids to hang out in the middle, in that sweet spot, right at the top, and be ultimate problem solvers. But what I love about this diagram, I think back and I look at the right side of the page there, and I think about gaming in particular, because gaming was always something I fought. After my grade 5 LTO, I ended up doing a prep coverage job in primary, but I've spent most of my teaching career in intermediate fighting games for the most part, because I always thought that running a tight ship in your classroom meant classroom control. Kids would be compliant if they were sitting in quiet rows and all doing the same thing through that one-size-fits-all model, which is completely counterproductive and contrary to what my entire webinar is about tonight. And when I started to think about gaming and looking at gaming through a different lens, and not simply playing games like Clash of Clans is one of the best games to teach financial literacy, but I used to fight it, but also having kids build games using math concepts that Papert would have loved to see, such as geometry, having turtles move around a screen to actually play a game, or thinking about Pacman from 1980, where Pacman himself or herself, Miss Pacman, rotates and translates across a Cartesian grid, and the ghosts move at random throughout these quadrants by changing their X and Y positions at random. So I'm going to bring it back to the beginning. What is coding? And there's a reason I'm telling you this, and my assumption is, and I should never assume, I suppose, but because this is called Beyond the Hour of Code, my assumption was most people had some experience. And I know for those of you from Superior Greenstone, you've had ample experience. We've been following it on Twitter with the Ontario Codes hashtag and all the wonderful things you've been doing with Lisa Floyd, among other people. So amazing. But I wanted to share about what coding is from a very simplistic, trivial level, because I think about some of the things that I've been doing in my language arts classroom for the last decade. And so if you can think about coding as a set of instructions that tells technology to do something, then it's no different than procedural writing. And so in my school board, we have a writing framework where we teach forms of writing kind of in isolation. We teach explanation writing, we teach procedural writing, we teach narrative writing, we do research projects, things like that. And so a few years ago, I thought, telling the turtle on Papert's logo to do something is a procedure. But for some reason in computer science, we call it an algorithm. So I started using the word algorithm in my intermediate class because I was finding as students came to me in grades 7 and 8, they were kind of disengaged with procedural writing. They'd been doing it for a number of years because it's in our writing framework with our school board. And I thought, it's so fascinating to think that even as early as 5 years ago, I would make all the students in my class write the exact same procedure. We would put a learning goal up. We would make success criteria. I would provide a rubric, and I would try and, you know, put kids into this box. I didn't care about equity. I didn't even think about kids who had peanut allergies and couldn't have peanut butter. I wasn't considering students that were gluten-free and really didn't even eat toast. I just had this expectation that everybody understood how to write a procedure for making it because I knew how to make it. And I thought, you know what, this is boring and this isn't the proper way to approach this. And so driving home one day, I just thought, what happens if we don't have bread? And so the next day at school, I said, okay, we're going to continue with our procedural writing pieces. And of course, grade 7 and 8 fell, and I thought, I've got to change something. I threw this up on the smartboard. I said, what happens if we have no bread? You know, and one student would say, well, you can go next door. We can go to grandma's house. We can actually drive to the convenience store if it's close by. And another student would say, well, I live on the farm, so I'm not driving to the convenience store. And we started talking about those equity pieces. Some people live in town and they walk to school, and some live way out of town and they don't walk to school. And I said, you know, what happens if we don't have any bread? And they started saying things, or sorry, what happens if the power is out? And they started saying things like, well, maybe there's a thunderstorm, and we eventually got to a place where it was about a zombie apocalypse. And I said, okay, everybody take out a piece of paper. We're going to do a quick write right now. Tell me why the power is out. I'm going to put the Smart Notebook timer up on the smartboard because that's totally engaging in those days. And I'm going to give you 3 minutes to write this quick write. And they were engaged in this. And I thought, wow, now we're doing small moment narrative writing to actually set up what we are supposed to do with our procedural writing. And what I realized through this process is, as a byproduct, I had taught conditional statements without even thinking about it. If have bread, then make toast. Else, get bread. And I started to think about how I actually coach my basketball team. I've been doing this the entire time. If you pass the ball to the point guard and an opponent approaches, and if a teammate cuts into the key, then pass the ball down low. Else, look for another open player. And so I actually started to take my class down to the gym just to prove that we could think algorithmically in any subject area. And I started to change how I taught my phys ed class. I'd always taught it through simulated play. I just started using the terminology that we find in computer science, but I really hadn't changed anything about that so-called traditional lesson. But when I reflect on what I had actually done, I had taken that very linear procedure and I had made it very three-dimensional, if you will. We've got this matrix now. And it made me think about purpose and audience and perspective. And it made me think about spatial sense and being able to think abstractly. Because in order to make a really deep flowchart, you have to be really good at chess. And chess takes, being a good chess player, takes a lot of abstract thinking. So I went back to my classroom and I started to think about everyday routines, because we're still studying procedural writing, of course. And so I picked on Monopoly. And so I threw this up on the smartboard and I said, if my turn and in jail, and my turn and in jail are both variables, and if both of those variables are true, so now I'm talking about algebra, and I'm talking a little bit about science, we're talking about dependent variables, we're talking about independent variables, that if both of those variables are true, then roll dice. And guess what? Roll dice is another procedure. It's a function. It's a module. It's an algorithm. Those words are all synonyms. It's another procedure. And that procedure is going to return another variable called roll doubles. And if roll doubles is true, then leave jail. Else, stay. And leave jail and stay in jail are also both procedures. Stay in jail has very few steps, but leave jail might have a little bit more. And I'm talking about this lesson in the staff room, and a colleague of mine in grade 2 said, let's do this. Let's team up. Our classes can buddy, and we're going to pick on a health lesson. And I thought, this is brilliant. So she had said, we have just finished writing the procedure for brushing teeth with her grade 2 class in a health/language class. And I thought, this is brilliant. So what we did is we grouped her students with my students, and we scaffolded this lesson. We completely removed the one-size-fits-all, thou shalt, everybody writes the same procedure. And we had put kids in strategic groups and called them functions or modules. And so we said, this group to the right, I need you to write the procedure, module, function, algorithm, whatever you want to call it. Write the procedure for getting your toothbrush. And have the conversation about where you each keep your toothbrush. Because we're talking equity here. Some keep it behind a mirror. Some keep it in a drawer. Some keep it in a cup on the counter. Talk about that. Write the if-then-else statements for getting a toothbrush. Now this group at the back, I want you to write the procedure for getting toothpaste. This group over on the left, I'm scaffolding it for this group. You're going to write a really simple procedure for simply brushing. Left, right, repeat. But you folks, you talk about how many times is appropriate to repeat. Do you repeat 40 strokes? Do you do 20? You folks figure that out. Put it on chart paper. Let us know what that looks like. The last group over to my left, and I'm pointing in my living room as if you can all see me. The last group to my left, you write the procedure for cleanup. And I looked at my colleague, mind blown. Completely biased because this was our idea, like it was the greatest procedural scaffolded lesson ever. But I said, as a class, we just wrote the algorithm for brushing teeth. But as individuals, they all had to provide mini procedures to pull this off. But here's the beauty. I said to my grade 7s as I walked around the room, I said, you know what syntax is? Some of them did, some of them didn't. I said, syntax is code. So if you write Java or Python, syntax is brackets and semicolons. If you're playing in Scratch, syntax is the blocks that you link together. I said, well, guess what? Syntax right now is the English language, and your syntax must be 100%. Or your module will crash with a syntax error. And if your module crashes, by the way, your module is get toothpaste. If you crash, none of us are brushing our teeth, and we are all going to be really unhappy with you folks. And for the first time, I had intermediate students care enough to go back and proofread. Prior to this, when I had made them all write the same procedure, whether it was making pizza or making toast, they would give me numbered steps full of spelling mistakes. And as much as I tried to make them go through a writer's workshop and revisit, they just weren't engaged enough to do that. But when I told them the English language was their syntax, and if it didn't work, they were letting everybody else down, and they didn't want to let their grade 2 friends down, they went back and they proofread. And I had never seen such accurate spelling and grammar in English written procedures before. So that was a big, big game changer in my classroom, because I was able to scaffold these procedures and differentiate and still be compliant to my school board by doing procedural writing, but not everybody was writing the same procedure. Although in some sense they all thought they were, because we were contributing to the same algorithm, that bigger picture. And we took it one step further and we put symbols up on the bulletin board. And each symbol represented a different module. And we went through scenarios using push pins and string, and we created this giant web, right? If we have power, then your electric toothbrush is going to work. And that was a string between pushpin and pushpin between two different modules. But what's so fascinating about this is we had a storm a couple of weeks later, and the boys in my class had come to me and said, Mr. A, we thought about you last night. Well, that's kind of weird. There was a hockey game on. Why are you thinking about me? They said, the power was out. We were thinking about that lesson while we were brushing teeth. And I was completely mind blown. Because the fact that they had told me that meant they had likely shared it at home and had probably told their parents about that activity, because they were reminded of it during a thunderstorm late at night before they were going to bed. And so through this unplugged lesson, something we've all always ever done, we've all taught procedural writing, particularly in a science class. This is just another way to look at it. We're actually teaching the fundamentals of computer science. We've taught conditional statements. We've taught Boolean logic. You know, we've taught if-then-else, we've taught loops, we had conversations about variables, and we talked about what syntax is. And it's been my experience now that by doing these activities early on in the school year, because we also teach math in isolation as much as we try not to, that's just sort of the way the curriculum is laid out, and because of report cards, we tend to do that. Our textbooks follow those isolated strands. When students get to the algebra unit, they're less confused about why letters exist in math in the upper grades. Prior to me teaching this way, kids would come to me in grade 7 and go, I have no idea what X is. And I would say, that's the point. We have to isolate it and figure out what it is. And they had no clue what I was talking about. But now it's been my experience when kids come to algebra and I say, okay, 3x plus 2 equals 5. We got to solve for x. And they go, what's x? I said, well, it's a variable. They said, oh. So there's information in it that I have to find. And I would say yes. And it's my job to teach you the algebraic rules to isolate that variable in order to figure out what that number actually is. So not only did this approach re-engage my traditional procedural lessons, I was able to go cross-curricular just in terms of vocabulary, which to me was enough. I saw the buy-in, so it was a great opportunity and something that you can take back tomorrow and do in pretty well any subject area if you're looking at procedural writing. The next example I want to talk about before we actually jump into Scratch is geometry. So I'm just going to see does that enlarge on your screen now that I've been talking nonstop for half an hour? Can you give me a check mark if that actually worked and it wasn't just a zoom on mine? Green check mark if you see it zoomed in, for those of you that are still here. X's. So, okay, that's bizarre. So maybe it only zoomed in on my screen. I'll go back to fit to page. The picture on the left in this example is from Kristen Whiting's class, who at the time was teaching a grade 2-3 class in Windsor. The picture on the right is from a grade 1 class in my school. A couple of years ago, I was working on a ministry project to create D2L content. What you see now on the EduGains site that the ministry has created, we were the first iteration of the team that started to put those resources together. And so Kristen and I were on this team, and we thought, okay, what does unplugged coding look like in primary? And let's just throw technology out the window because we don't want there to be an excuse, I guess. So let's figure out how we can do unplugged activities. And immediately we went to geometry and we looked at location and movement. And what she had done in this activity is she had taken her carpet in her primary classroom and she had created this grid. And she had started using words like cells. B2 is a cell, and she was talking about location and placement on this grid. And then as a class, they created pseudo block code right here. So can you see right 90, forward 4, left 90, forward 3? So they created this pseudo block code. So there was no syntax. The students just had to link that code together. And they stood around this carpet, and she had strategically placed objects because she knew she wanted to scaffold this lesson. So she had some students in proximity closer to some objects than other. Those students that needed classroom enrichment, well, they were on the other side of the carpet because she knew that their procedure was going to be more challenging. And all they had to do was kinesthetically walk through this carpet after they had created their code, their procedure, their algorithm. So you see them here with clipboards. They're all trying to write down what they think the script would be to move from point A to point B throughout the carpet to retrieve whatever the object might have been. And then one student would actually act it out kinesthetically, which Seymour Papert would have loved, and the rest of the class would have followed along to see if they were actually correct themselves. The example on the right is a phenomenal example of spatial reasoning. And if you've read the ministry document that our ministry put out, I believe, I think a year ago now, winter 2005 possibly, it talks about the importance of spatial reasoning as an early indicator of future success in mathematics. And if we can really focus on spatial reasoning and spatial thinking as a skill in primary, then our students will be able to think critically and think abstractly later in life. Now, Jessica Konechny, grade 1 teacher in my school, she had said, I want to do the hour of code, but I have one tablet. What can I do? And I said, well, like Seymour Papert said, and like Reggio Emilia, the environment is the third teacher in your classroom. So that tablet is going to be the teacher, and you're going to be the facilitator. So what she had done is she had loaded the app Lightbot, which is an app, a procedural app, where you tell a robot to move from point A to point B through a three-dimensional space. But the problem when you connect a tablet with that app to a projector is its perceived depth. Right? We see a robot moving back and forth left to right, and we see what appears to be a robot moving forwards towards us in that third dimension, but the screen itself is flat. So she had got the linking cubes out, and she projected the app. And if you're familiar with Lightbot, the terrain is actually made up of cubes. It looks a lot like, almost like Minecraft blocks, if you will. So she took these linking cubes, and she said, I want you to actually build the level first. look at what you see on the projector, projecting off the one tablet we have, and build this level. And you'll notice the brown block here on the right side of the image. They used symbols from the app, and they used whiteboards to create the procedure. Abstract thinking, spatial reasoning, computational thinking, all of those sort of buzzwords. They would create this symbolic procedure to move the brown cube and plunk it on the blue spot on the far left. And the beauty of this activity is because the tablet is doing the work, it frees up her time to consolidate with students. Some students who are perhaps high flyers and grasp the concepts so quickly, they would move the brown cube to the blue spot, get it right, but they would have to go up to the tablet and try it. And the tablet was giving them the feedback. The tablet would say, no, you're wrong. Perhaps you should go back and try this instead. Or maybe one of your turns was wrong, which Seymour Papert would have absolutely loved. And so those students that were perhaps a little bit slower, well, she was able to actually sit with them and do the observation and the conversation that growing success says we are allowed to do when we assess and we evaluate our students. So I thought this was a significant game changer in terms of rather than pushing a mobile cart to a classroom and having all kids play on Lightbot, she would do one level at a time, but they actually had to build it too. The kinesthetic, the tangible piece of assembling the terrain using math manipulatives, I thought was just an absolute brilliant example. So when we came back together as a group working for the ministry, we thought, okay, what does this look like just in terms of location and movement and geometry, because we have that existing math curriculum. We created this kind of pseudocode just to offer sort of a continuum from K to 8. And really the location and movement doesn't change. It just, all we do is we advance the sort of syntax code to include more as we progress from left to right down this continuum. So I thought, what does this look like in intermediate? We don't have a carpet. I could use the tiles on the floor. I have done that. I've moved desks and I've used tiles on the floor. But I thought I have a bajillion pieces of graph paper that I photocopied once because we had a paper policy, right? I know you've all been there. Some of you are smiling, where we only had so many pieces of paper we could photocopy in a given year, and so teachers were stealing it from each other. If you left it in the photocopy machine, it was gone. There was this underground black market of paper. Teachers were selling it in the staff room. It was amazing. Anyway, I had all this paper. I thought I better photocopy some grid paper because I've got leftover paper at the end of the year, and I know I'm going to use grid paper in the following years, and that certainly wasn't the case. But anyway, I thought I'm going to use this stuff up. Kids don't dislike paper, and there's nothing wrong with doing a paper and pencil task. So I projected this on my smartboard. It was a Friday afternoon. The bell had rang at lunchtime, and I was not nearly planned for anything at the end of the day on a Friday, much like the rest of us, I'm sure. And so I put this piece of grid paper up on the smartboard, and I drew some arrows, and I said, all right, write the procedure to move the robot from point A to point B. Before you do that, tell me what quadrant the robot is in. So a few students would raise their hand and say the robot's in quadrant 2, right? Because we go counterclockwise. That's intermediate math. And I would say, you know, what quadrant does the robot end up in? And I'm trying to do these teachable geometry lessons before we can get into actually writing this pseudo-code location and movement procedure. And I wanted to raise the awareness that moving this robot is no different than brushing your teeth. We're still doing a procedure. We're just kind of doing it in math class now. And I'm being a little contradictory here to my own beliefs in terms of the one-size-fits-all. I did project this. I wanted everybody in my class to do this activity so that we could come back together so that they all had the same experience. There's only one way to solve this problem. It is by no way wide walls, low floor, high ceiling. It's not really rich in any capacity. And in fact, it's not much different than the hour of code you find on code.org. Now, code.org this year introduced the Sandbox, where you can do whatever you want in that space. But early on, it was very scripted. There was only one way to sort of solve the problem. So what I did then is I gave them all graph paper, blank grid paper, and I said, unlock the chest. Write the script, write the procedure to open that chest. And now there's more than one way to solve the problem, so I'm offering opportunities for all learners to feel success, because now we are talking wide walls, we are talking low floor, high ceiling, whatever buzzword you want to put on that. But after that, I then had students create their own game. And this was where I started to shift my pedagogy in terms of how I assess and how I evaluate. Because here I am now providing opportunities for success for all learners to develop to the best of their own ability. And I started to think about the evaluation piece. Certainly the students in my class who are on classroom enrichment had created some pretty advanced games, but the students in my class that were on IEPs, perhaps not working at grade level, had also created games. Yes, they were a little bit simplistic, but they were to the best of their ability. And as far as I'm concerned, I had to rethink how I graded that. I had to remove the rubric because we weren't all doing the same thing. And I think about Genius Hour, and I think about passion projects, and I think about play-based learning, and I think about how those opportunities don't allow for a sort of predetermined standard of learning. I was at a loss as to how to evaluate this, particularly in the intermediate grades where you have to actually assign a quantified number. Is it a 72? Is it a 77? And I started to think about the notion of time at school. For so long, time has been the constant. We put kids in isolated settings, we start a timer, and we judge them based on what they're able to produce at the end of a period of time. And I thought, it's not like that anymore. I mean, there isn't an educator in the world that doesn't believe all kids can achieve, and if we believe that, then perhaps grades needs to become this new constant, and tools and technology and time needs to become this floating variable, because some students in my class, they needed a lot more than 40 minutes to build their game on grid paper, where some students perhaps were finished in an hour, and that was okay. I wanted everybody to feel success with their product, but I was also assessing and evaluating the process of learning, which growing success says is equally, as important. And it starts to make me think about the mathematical process. And it's really, okay, I'm going to put everybody on the, no, I won't put everybody on the spot. That's not appropriate. The mathematical process, I tend to ask people when I'm sharing this slide live if they'd ever seen it before. And quite often, not a lot of us have, myself included up until a few years ago. And the reason is we always skip over this page. This page is at the beginning of every grade in our current math document. And I'm guilty of skipping it because I go straight to the expectations because that's where I'm to report on. And so we don't focus enough on the mathematical process. But what's so fascinating to me about the mathematical process in terms of our math document in Ontario, which is a phenomenal document. I often hear, it's old, it's 2004, 2005. Well, it has the word computational strategies written in it from 13 years ago. Our interpretation of electronic tools to solve problems has perhaps changed, and now that we use things like Scratch. But the fact that the word computational strategies exists gives it a lot of credibility and a lot of merit. And I think if we can focus on the math process, and if you think about that tip of the iceberg metaphor in terms of student product is the 10%, it's the 90% blood, sweat, and tears that went into it that's equally as important. If not more important when we're evaluating, when we're assessing and evaluating this process. And I also think the math process lends itself incredibly nicely to the learning skills we have in Ontario. And as an intermediate teacher, I no longer look at report cards because the front page tells me everything I need to know. If they're E's and G's on their learning skills, I don't need to open it to know their A's and B's. On the other hand, if they're S and N's on the front page, I also don't need to open that report card. So it makes me think about focusing on the process of learning. And that process will take longer for some students, and that's okay once we remove time as that constant. I'm going to jump ahead back to the Venn diagram and bring it first full circle because I really like to use computer code to do simulating, automating, and gaming in my classroom. And I want to share one more aha moment that shifted my pedagogy in terms of computational thinking. And it involves Minecraft. And so I put this growing pattern up on my smartboard a few years ago, like I had done every year. And of course, the expectation is we're going to create a table of values. We're going to extend this growing pattern either using our words or by creating an algebraic expression. And so just so I know I'm not talking to nobody, let's use the chat box. Can you use your words to describe how this pattern grows? And I'm just going to mute my microphone, so don't think we've disconnected. But let's just spend about 30 seconds. If you could just write in the chat box, use your words, how does this pattern grow? So you all saw it grow the way I saw it grow. And 4x plus 1, Stephanie Blair, nice to see you, is exactly the pattern that I was going for. So we had created our table of values, and we had created this algebraic expression. And what's so fascinating to me is the one student in my class at the back, and I hate to profile kids, but we'll say grade 8 student, headed to the applied stream, typically disengaged at school, raised his hand, and he wasn't trying to be confrontational. He just said, Mr. A, you're wrong. So what do you mean I'm wrong? He said, you just asked us how we see this pattern grow. And I said, well, yes. And he said, you just made a table of values, and you just made a pattern rule, and you know, if we don't see it that way, we're wrong. You're going to give us a rubric, and we all have to get the same right answer because Malthus is evaluated as correct or incorrect. And I said, what are you getting at? And he said, I've been playing on my phone this whole time, and this is what I created. And it blew my mind, because our kids live in a third dimension. And when you talk about spatial thinking and computational thinking, he did not see that pattern to grow. We all saw it grow. And the expectation was that they had to see it grow the way I saw it grow, or they were wrong. And when he showed me this picture, it almost brought me to tears, because I realized there's almost an infinite number of ways to extend this growing pattern when it grows up. And I said to him, I said, tell me about this constant 1 purple. You agreed there was constant of 1 purple. He said, no, Mr. A, there's not a constant of 1 purple. It's buried. Here's the cross section. And I was completely mind blown. So immediately I thought about what I was doing in geometry, where I wanted kids to create their own games, the wide walls, low floor, high ceiling. I said, everybody in the class, stop, grab a device. I want everybody to create a growing pattern right now, or to create this growing pattern as you see fit. I want you to make a table of values. I want you to use your words. I want you to tell me how it grows, and then I want you to bring it up and have a conversation with me. And all of a sudden, everybody in my class was able to create a product and come and have a conversation with me about how they saw it grew. And as long as the table of values matched what they had actually built in Minecraft, I was beyond ecstatic. But the reality was just about every one of them was able to do this. And so it goes back to what I had said earlier. I started to just think about, how can I not give them all, you know, that constant B, every 75? Like, what does this look like? How do you quantify something that's so open-ended, where everybody in the class is able to create a product to the best of their ability, and then come and talk to you and tell you about it while they're exploring their own creativities and their own curiosities? I'm going to share one more example before we actually dive into Scratch, because I'm sure a lot of you are here to learn about Scratch as a tool, and thank you for listening to me share my journey from where I started to where I am now. This last story is a complete game changer. When we talk about simulating, and I know, Mr. Carruthers, you've seen this one before, but bear with me, it's one of my favorites. When we talk about computational thinking and creating simulators, this is an example. I was teaching probability the more, air quotes, traditional way. A few years ago, I'd given every student in my class a penny. I thought, I'm going to be that really cool, hip intermediate teacher that gives everybody a Canadian penny because they're going away. And so I had everybody pull out a piece of paper and create a flip chart. Flip chart. Thinking coin flips already. A T-chart. I said, I want everybody in the class to flip the coin once. Don't do anything. Don't say anything. Tally it in your T-chart. Okay, now, raise your hand if you were heads. And, you know, I had something like 24 students in my class at the time. So I said, look around, everybody. We have an immediate data set of 24. How many are heads? How many are tails? And it was approximately 60-40 that day. And they were saying that. They were recognizing that. They said, you know, it's not quite 50-50. And I was prompting them, like, what should it be? You know, in theory, I'm teaching theoretical and experimental probability. It's grade 7 math. You know, the more times you run the experiment, in theory, the closer it should get to, the experimental should get to the theory. So, in a nutshell, if you could flip a coin 1,000,000 times, it would be 50-50 to the umpteenth decimal place. And it's my job to sort of teach this. So I said, I want everybody to flip it twice. And don't say anything. Just look at what you got. Think about what you got. Some of you are 50-50, and some of you are 100% one way or the other. There are no other cases. Some of you are 100% heads, some of you are 100% tails, and some of you are completely 50-50. But we all should be 50-50 in theory. And then I said, here I am, Mr. A, the magician. You're going to flip this coin one more time, and I guarantee you, none of you are 50-50. And sure enough, a few of them in my class roll their eyes at me like, you're such a tool. And a few people in my class are like, well, I'm going to prove them wrong. So everybody flips their coin, and they're looking at the results. And when you flip one coin 3 times, it will never be 50-50. It will either be 100% one way, 33% one way, or 66% one way, just because of the nature and the beauty of mathematics. And so I said, okay, I want everybody to flip their coin now. Work with a partner. I want you to flip your coin about 20 times. And I'm going to put up that wonderful, totally engaging Smart Notebook timer, and we're going to let the clock run down for 3 minutes. You only have 3 minutes to flip this coin 20 times. It doesn't matter if it takes 7 minutes for some of you. That was the way I was teaching right then. Everybody's going to do the same in the same amount of time. Okay. So I'm walking around the room, and I realize that there's a group of girls to the right who have taken out a novel because they would just much rather read. They looked at me. They said, Mr. A, I want to read my book. I know it's going to be 50-50. Yeah, I get it. And I was like, no, I really need you to do this, please. Could you please do this for me? I'm walking towards the back of the room, and I see boys whipping pennies at each other. And in my peripheral, I see another student asking people for their pennies, like, can I have your penny? Can I have your penny? Because he just wanted to have so many, last Canadian pennies. And I thought, this is going absolutely terrible, but I have no idea what else to do. This is what the Nelson lesson told me to do, so I have to see this through. At the end of the lesson, I had a student approach me and say, Mr. A, I'm going to make you a coin flipper simulator so you can teach probability better. And he said it just like that. And he didn't mean to be rude. He was a student with a learning disability, I think he was grade 8 at the time, heading to the applied stream. He wasn't meant to be rude. Communication was where he sort of struggled. He said, Mr. A, I'm going to make you a simulator so you could teach probability better. And I said, what is this simulator going to look like? He said, it's quite simple. In Scratch, there's a built-in procedure that will allow you to pick a random number. I'm going to tell it to pick a random number between 0 and 1. I said, why 0 or 1? He said, it's because it can only be 0 or 1. So in that moment, it was a teachable moment. I said, we call those whole numbers. He goes, oh, yeah. I said, do you know what an integer is? And then he could tell me. I said, that's wonderful, a little teachable moment in our conversation. It can only return 0 and 1. I said, okay, so if it returns 0, then show heads, else show tails. And I was completely mind blown, but he was like, you taught me that when we brushed our teeth with the grade 2s last week. And I thought, okay, you need to do this. And he said, can I do it at school? And I thought, I have no idea. I don't know if that would be okay. By today's standards, absolutely 100%. He had found a passion project in math class. But at the time, I was like, I don't know. We have some textbook work we have to get through tomorrow. Anyway, I let him do it. And it took him a long time. He came in on a Friday with some of his friends. He said, Mr. A, it's done. So what do you mean it's done? So by the way, why are you in school early on a Friday? You guys don't even want to be in school to begin with, and you're here early. So it works. I said, you're kidding me. Come on. What do you want to do? They said, we want to flip it 1,000,000 times. I thought, yes, we do. So we put their coin flipper simulator up on the smartboard computer. We dedicated the smartboard computer to their app for the whole day. And it was the biggest metaphorical fridge I had ever seen. They had never They've never had their work sort of, in a showcase in the 9 or 10 years they had spent in elementary school. And I still get goosebumps telling the story because they were beaming from ear to ear when the rest of the class came in when the bell rang at 8:30, and they said, "You did it! Wow, we're actually going to watch this thing." And they were so proud. And I thought, oh, please let this thing work. Please tell me I didn't just throw them under the bus. So I fired it up. You'll notice here that there's a turbo button. They said click the turbo button. So I'm going to try and do a screen share now. That's my last slide, and we're going to cross our fingers that for the last half an hour we can do an application share. So I will no longer see Blackboard, but I will still hear sounds. So if you raise your hand, can you try and do the raise your hand now just to confirm I hear the ping? Ping, ping, there it goes. Great, okay. So if something is not working or it's just becoming problematic, can you please ping me? If I do this, you will see a black box. If I do this, you should see Chrome. Can you confirm that, Mallory?
Yes, we can see it perfectly.
Oh, wonderful. Okay. So here's what's super cool about this, because not only did this student create a simulator to demonstrate theoretical probability and the law of large numbers, he had to use algebra and geometry to do it. I said, explain to me what these things are on the left side. He said, those are variables. You told me if I flipped the coin 1,000,000 times, it would be 50-50. So I created variables to store that so I could actually prove you wrong. I thought that's pretty funny. So he understood what variables were in terms of placeholders of information, and he used these principles. And I said, you know percent heads? I said, how does that work? He said, well, it's simple. It's heads divided by flips. That'll give you the experimental probability. I said, that's pretty neat. We call that a dependent variable. Heads is dependent on what's returned randomly, but percent heads is dependent on heads, and we would call heads the independent variable in this instance, because that was a little bit of my science curriculum. He thought, oh, that's pretty neat. Yeah, that one affects what that one does. I said, exactly. He said, you know, I wanted the coin to actually make it look like it was flipping. When I started to do this initially, the variables were changing, but I wasn't seeing anything, and I thought it was boring. Like, I wouldn't download this in the App Store because it doesn't look very good. So I wanted to create an animation. I said, how did you do that? He says, well, I made the T, the H, and the T in the circle. I made it go up and down to make it look like it was actually flipping. I said, how did you do that in Scratch? He said, it was easy. I kept X the same, but I changed its Y position. And I thought, this is absolutely amazing. Here I have this student who told me he's going to build me a simulator so I could teach probability better. And he used geometry and algebra to create an app that will show the theoretical and experimental probability and demonstrate the law of large numbers. So here we are in front of the class. Friday morning, they said, click the flag. I clicked the flag. You see the animation? It was one flip. It returned heads. And so we're at 100% heads. I said, click it again. I clicked it again. We're at 2 flips. We're at 2 heads. We're still at 100%. I said, boys, it didn't happen like this then. It was a different result. I said, boys, there's a bug in your program. That should be 50-50. They said, no. It's the experiment. Refresh the page and run it again. You'll get different results. And that, to me, meant they had not only built the program, but they had run the program more times over to prove the results were truly random, which became a teachable moment. I said, boys, if your app had returned the same results every time, you would have a biased coin. And they went, oh, that makes so much sense. I said, do you remember when we were talking about having a weighted die or dice so that you would roll a 6 or snake eyes more often? Those are biased dice. I said, because your coin truly returns random data, it's not a biased coin, which is a whole other lesson, right, in my textbook. And I thought, this is absolutely amazing. They said, okay, Mr. Drake, go ahead and hit the turbo button. And sure enough, it will prompt you, how many times do you want this coin to flip? They said, put in a really, really big number. So I put in a really, really big number, and I pushed enter and just watched them beam from ear to ear. And so I'm going to push enter now, and the coin itself is not going to animate. They told me that they had to remove the animation because when it tries to do that 1,000,000 times, it causes your computer to get really laggy, which I thought was fascinating in terms of the process of learning. So they actually had to strip down their animation. So I'm going to push this flag, and all I want you to do is keep an eye on these variables on the left side of the screen. So we're already at 500 coin flips. We're almost 50-50 already. And we left this thing on the smartboard, and I was so proud. And we have a lot of Rotary at my school. And it was so fascinating to watch kids in my class ask to get a drink or to go to washrooms in other classes because they were sneaking out to actually come and see what this thing was. They didn't want to go outside at recess. And I thought, these students are incredibly engaged in what would have been a boring flipping of the coin lesson. The fact that they kept coming back. It was such a powerful story, especially for the creators of this game. And it didn't actually hit 1 million by the end of the day, but it was like 725,000, and it was 50-50 to about the 7th decimal. And I just looked at them and I said, that's the law of large numbers. And they said, cool. And they went home and we never really talked about it again. But it was such a powerful moment in my own teaching. And I'm going to ask you, how do you quantify a product like this? Now, we got to have conversations, and I made observations, and I had a lot of anecdotal evidence that I could put in their learning skills as they built this thing. But they've created a working product that demonstrates almost the entire strand of probability, and I struggled with the evaluation part. I struggled with the reporting part of what we're responsible to do as educators. So that's where I am in my professional practice, is trying to understand how to quantify something like this. Do I have to quantify something like this? You know, is it a disservice to then put these kids back in a testing environment and ask them to demonstrate what they'd already done? Well, they have created a simulator that demonstrates mastery of probability. And I totally agree with the descriptive feedback piece. I think evaluation hasn't quite caught up to 21st century pedagogies and teaching and learning. I think we've got work to do in terms of what that looks like now, what that looks like in the 21st century in terms of grades. I mean, there's a big movement across North America to throw out grades. There's a lot of places in Canada, in fact, that have gone gradeless. And I'm using the air quotes again when I say gone gradeless. It means there's still grades on report cards. It means they've removed grades on a daily or a weekly basis. It's become those anecdotal check-ins, and it's become the descriptive feedback. I mean, it's fascinating to me to think about, if you never tell a student in primary, say grade 2, if you never tell a student in grade 2 they got a level 2 in math, then just maybe they won't dislike math. I don't know. Maybe they'll just see growth, and they'll just see movement, and maybe they'll perceive math as fun if they don't think they're bad at it. So I don't know. That's where my research is sort of going now, and I would love to have a conversation with you at some point in the future about your thoughts on that. Lastly, why most of us are probably here. We want to not just listen to me, but to play in Scratch. So if you want to follow along with, we're going to actually create a quick coin flipper. I actually don't even use the coin metaphor anymore. I call it truth or dare, because grade 8s and 7s seem to think truth or dare is they don't realize I'm totally tricking them. It's still a coin flipper, but they think it's totally awesome because we get to play truth or dare. So if you want to follow along in a web browser on a machine that is Flash-based, so this will not work on an iPad, then head over to scratch.mit.edu in your browser. Amy, I'm all over having a conversation with you. I'd love to do that, either email, Twitter, or even a Skype chat at some point, or even face-to-face at a conference. So head over to scratch.mit.edu, and you're going to want to click Create. And it'll bring you to the default Scratch page. You don't actually need an account to create in Scratch. You do need an account to save in Scratch. So you'll see the cat is in the center of the screen, and I actually use Scratch to teach geometry. As I move my mouse around, you'll notice the X and Y coordinates are changing. It's actually tracking the position of my mouse. When I first introduce students to Scratch, I will often ask them to put their mouse at the origin. For those that don't know, I will explain to them, of course, that the origin is position 0, 0, and it's always fun to try and watch them put their mouse right in the middle of the cat because it's actually tracking pixels as the unit of measure, and because they're so small, it's a little bit challenging to actually get to 0, 0. But I want you to notice in the top right corner of the screen, it shows you the position of the cat. So the cat is, in fact, right on the origin. So I might say to grade 7s, quick diagnostic, put the cat in quadrant 2. And I would expect them to do that. I might say approximately put the cat at positive 200, negative 100. And I would expect them to be somewhere down here. But for those that don't know, they're going to be moving the cat while tracking its location, thus constructing their own knowledge of the Cartesian plane, like Piaget and Papert had said, by simply playing in Scratch and moving the cat around. Some students would have said, yeah, it's somewhere in here and stopped. Other students would have literally dragged it along until they actually got to the position that I had asked them to be in. I would also say if you move the cat to the left, what do you notice about the x value? If you move the cat to the right, what do you notice about the x value? As you drag the cat upwards, what do you notice about the y value? And as you drag your cat downwards, what do you notice about the y value? So Scratch allows me to spiral my curriculum. It uses geometry as the tool, like Papert's logo back in 1967. It uses geometry as a tool to engage kids and create content. The categories in the middle of the screen are just that. Under motion, this is the built-in blocks that we would use to move our character across the screen. You can change your sprite at the bottom. You can pull from internet images. You can take pictures from camera roll. Or you can use sprites from the built-in library. Each sprite has its own procedure or its own set of code. If you think about the original Pacman game, the game would be quite boring if all the ghosts behaved the same. And so each ghost was coded differently. Each ghost had its own script, its own procedure, its own module, its own algorithm. And so that's what the sprite's pane is about at the bottom. So because we're down to about 15 minutes, 10 minutes before the wonderful survey at the end, we're just going to do, just the cat is going to randomly tell us to do truth or dare, and we're going to tally it. So what I want you to do is head to events. You're big, smart people. I'll let you look through the categories on your own. We'll just build this simulator for the sake of time because it is being recorded and people will want to come back and look at it at the end. So drag over a when green flag clicked. Everything in computer science is event-driven. Your Facebook timeline does not update unless a human posts. Computers and technology, I tell kids, computers and technology are actually quite dumb. They just sit and wait. They don't do anything unless we tell them to. We are making significant advances with artificial intelligence, but the reality is a web page will remain as such until a human does something to change it. So when green flag clicked is going to be the event that actually starts our procedure. And what we want to do is head over to control, and we want to grab an if, then, else. Because we're only using two conditions here, we're talking binary, we're talking heads or tails, 1 or 0, we can use if, else. You could extend this later on and have students create simulated die rollers. They would just use a series of ifs, if rolled 1, if rolled 2, et cetera, but we're going to use the if, then, else. Okay, and you'll notice that those actually link together quite nicely. You'll see the hexagon shape between the if and the then. Scratch is nice that way. Certain shapes don't fit in there. You'll see the weight does not want to go inside that. It's not the same shape. But under operators, where you see all of the math, we do have these hexagon shapes that actually do fit inside of there. You'll also notice the pick random. So I want you to drag out a pick random. And teachable moment now, I'm going to say to the kids, okay, we're gonna change our range. This is a range inclusive of 1 to 10, and it's only whole numbers. We're going to change it to 0 to 1 because 0 is in fact a number. It is a placeholder in computer science world. Pick a random number between 0 and 1, and it can only be 0 or 1. And you'll notice that that also doesn't fit inside the hexagon because it's more of an oval. So you want to actually grab an equal sign because we have to make the comparison now. Remember when we talked about making toast? If have power, then, or if have bread, then make toast. Well, what we're going to do is you're going to grab the pick random, and you're going to start on the right side and pull it to the left and let go when you see that box highlight, like such. And so now we've got pick random 0 to 1. And on the right side in that box, you're going to want to put a 0. And pick random is a sub-procedure. It's built in. It's a sub-function. It's a sub-module where the computer actually uses the system clock to the whatever infinite decimal place to actually plunk a random number out. And so this shape, grab it by the equal sign. If you grab it by the pick random, you actually pull it out, grab it by the bottommost layer, and plunk it in there. So if pick random, which is a procedure that will return one of these numbers, if it returns 0, then 0 equals 0 is true. So then this portion of the code will run. If pick random returns a 1, then 1 equals 0 is false. And we'll jump down and run the else portion. So what we're going to do now is we're going to have the cat just scream at you. So head over to looks. Deanna says we lost sound. Check, check. Oh, okay, she must be trying to jump back on. Okay, so head over to looks. Thank you, Frank and Karen. And pull out 2 of the say hellos. Say hello. The first say hello, you can have it say whatever you want. I'm going to say truth. And the second say hello, I'm going to have it say dare. And you're going to want to grab that first one and put it in the top C part, the if section. And you're going to want to grab the else part and put it, put the dare under the else part. Okay. Now go ahead and click the green flag. I used to say to kids, save often, but now we have autosave. Now I say debug often. It's so much easier to find errors, logical errors, and syntax errors, and semantic errors in your program when you check it often. So run the flag. Click the flag. I got truth. What did you get? Spit it into the chat box. Did you get truth or dare on one click? Uh-oh. There's the dare. I was going to say we have a biased set of cats here tonight. Truth 3 times. And I'm glad you pointed that out, Stephanie. It's a great opportunity to have kids draw tree diagrams or make organized lists if you are an intermediate teacher. Dare on the 4th. Wow, your cat's completely biased. Okay. Where are we at? 8:43. I just want to show you the algebra portion of this. Let's make a tally that will keep track of the truth or dares, and let's program a reset button. So head over to data. You want to click on make a variable and call it truth. My pick random won't become a hexagon. Okay, the trick, Sandy, is if you try and plunk it in, if you approach from the left side like this, it doesn't work. Scratch is finicky. You have to start on the right side and pull it back to the left, and you'll see now that it highlights white. They've done that intentionally. I'm not entirely sure why, but trying to link code by approaching from the left doesn't work. But if you approach from the other side, it'll drop in there. Make a variable, call it truth. Repeat that, make a variable, call it dare. So you should have 2 variables like I have at the top. They're both set to 0 by default. And you'll see these pieces of block code appeared now that you've got a variable created. You're going to want to grab change, and you're going to want to grab 2 of them. And there's going to be a drop-down menu. You want one of them to be truth, and you want one of them to be dare, like I have here. So change truth by 1. Go ahead and put that above the say command, and put the change there above the, oh, not there, above the there command. If you've done this properly now, you should have created the counter for you so that you don't have to do it yourself. So when you click the flag, I'm 3 dares in a row. There we go. 1 truth and 3 dares. Okay. All right. Well, looks like we still have about 10 minutes, so let's have some fun. So make another variable and call it %truth. Make another variable and call it %dare. Okay. Make one last variable and call it total. I hope I'm not going too fast. All I've done is created 5 variables: truth, dare, %truth, %dare, and total. How do you get to make a variable? Deanna, we are under the data category in the middle. Bye, Leslie. Thanks for joining us. So you're on data in the middle, and then you click on the make a variable button. No problem, Deanna. No problem at all. Okay, this is where it can be a little bit confusing. I'll try my best to go slow. What I want to do is I want total to be the sum of truth and dare. So right now my total would be 4. I just want total to be a tally of the number of times the program has run, because I want to go truth divided by total would be %truth, right? That's my experiment. So I want, these will be decimal values. So what I want to do is you're going to grab the division, actually grab 2 divisions, which is the backslash in computer land. Kids don't know that, which surprises me still. The asterisk as multiplication and the backslash as division. I just tell them that this is a fraction and that it's the numerator divided by the denominator, and they typically tend to get it after the fact. I want you to head back over to data. I want you to grab truth and put it in the first circle of the first division. Grab a dare and put it in the first circle of the second division. Grab a total and put it in the second circle of the first division. Actually, going to put it in both. Truth divided by total and dare divided by total. Okay. You're going to need now, just move those off to the side for now. You're going to need 3 sets. 1, 2, 3. I forgot one operator, so head back over to operators and grab the addition. We have to actually find the sum of truth or dare. Okay, once you've got the addition, then you can head back over to data, and you're going to want to put truth plus dare in those appropriate circles. And you're going to want to grab that one by the addition and put it in the circle beside the first total. Thanks for coming, Patricia. Okay, so we have to set total to be the sum, of course, before we can do any kind of dividing. If you place the other ones in the appropriate spots there, then you should be good to go. So I'm going to click my flag, and you'll notice that I have a mistake. Here it is right here, my drop-down menus. You'll notice that my truth, my %truth, and my %dare did not increment. I have to change this to %truth and I have to change this to %there. So that's a bug, and that's a teachable moment I would have with kids. It's not a syntax error, it's more of a logical error because I was incrementing the wrong variables. But now when I go ahead and click the flag, I am 3, 3, 0.5, 0.5, and 6. I'm actually exactly where I should be. And on that note, I think I better stop there. I don't think we should add to it. We can take a few minutes for questions, and I know Mally will have a survey. The surveys are tremendously important to OTF in terms of getting more funding to continue to do these awesome webinars down the road. So if you want a screenshot of my code, grab it with your phone right now, or because I'm going to head back to Blackboard and turn off my application sharing. Turbo button is a phenomenal idea. Let me just, I'll tell you quickly how it works. The students had taken all of this code here, the if, and they had gone over to control and they'd put it in a loop. So it ran really fast. I'll do it quickly. I'll put the if in there, and I'll put the repeat up to the top. So when I click this flag, it's going to run this algorithm 10 times. So right now we're at total 6. It should be at 16 after I click this flag. But the cat's gonna say it each time now, but it's gonna run by itself. So the kids can actually watch it become 50-50. And actually, because the cat is speaking, it's slowing it down from the coin flipper simulator that I had sent. So that's pretty neat. Okay, I have 8:53, leaving us 7 minutes for a couple of questions, and then, of course, the final feedback. So I'm going to stop sharing. And I'm going to pass it back to Mally.
Thanks, Brian. Yeah, that is so cool to be able for the students to be able to really take control of their learning like that. So as Brian said, we have OTF would love you to fill out a survey on tonight's session, and there are 3 ways that you can access it. One way is by having by clicking on the link, the blue link. This is one of the only live links that are in the presentation. The second will be when you log out, it will automatically take you to the feedback survey. And the third one is I'm just going to put the link in the chat so that you can access it that way. The other thing about the feedback survey is, as Brian says, it's really important for us at OTF Connects to have the feedback and also to send the information to the Ministry of Education who funds these programs, and also to to Brian so that he'll be able to see the feedback about his session. The other, I'm just going to go on into the slides because I just really want to be respectful of your time on such a busy night. As we said, this is the very first session of 2017. There's some more sessions coming up for the rest of January and planned into February and the beginning of March before the March break. Isn't it nice to be able to say the March break? So please check the OTF Connect website for those sessions. And a couple other reminders. The Ministry of Education has given a subsidy for OTF members to complete to register and complete the programs of AQ programs for math, technology, and kindergarten, and that's on the OTF Connect website as well. And please tweet out any information or anything exciting that you heard tonight on any of the social media. There are the Twitter feeds, the Facebook page, and the YouTube channel. And one thing that I know is really helpful to teachers, especially if you needed to leave early or if you missed part of the webinar, is that we'll be sending out the list of resources. So anything that Brian spoke about tonight, a couple of the authors that he talked about, I've put their website in there, and that'll be coming out in an email in the next couple of days, also with a link to the recording. So thanks again for everyone who came tonight, and I'm going to go back to the feedback survey link, and you know, we really encourage you to finish that up, to fill that out. And the other thing about the feedback survey is once you've finished it, you'll be sent a link to a certificate for your professional portfolio. So that's just a thank you for spending the time with us.